So here we're going to work through two examples of linear regression. So recall that in linear regression, you're fitting x data to y data using parameters b. And so you want to express y as a linear combination of a sum of each parameter b times a different variable, either x1, x2, and so on. And you can express all the b variables together as a vector, b, and the formula for b is the following. It's x transpose x inverse times x transpose y. So this is kind of a messy relation. We're going to work through two examples here to show just what this means, what the matrix X is, what the vectors y and b are, and how you put it together to generate a fit. So first we'll start off with some data. Suppose you have the following xy data and you want to determine how they're related. Let's plot them. They look something like this. And you decide, well, I would like to do a quadratic fit for this data. I would like to fit it to some function y equals ax squared plus bx plus c. And I want to find out what a, b, and c are. So what we can do is in red here we have the different parameters of the fit, a, b, and c. And in blue we have the variables. We have an x squared, an x, and there's nothing multiplying by c. There's no blue number next to c, so really we can think of that as just 1. So it's ax squared plus bx plus c times 1. So what does this matrix X correspond to if we want to fit our data to y equals ax squared plus bx plus c? Well, the rows of X are going to correspond to the individual data points, and the columns are going to correspond to the different variables, or in this case, the different functions of X, like x squared, x, and 1. So the first column is going to be all our x squared data. And our second column is going to be the x data. And the third column, since c is just multiplying by 1, is just going to be a column of 1s. So that's our matrix X. The array Y is just our Y data. So now we have this matrix X and the array Y, which is everything we need to find B. So if we plug that into our formula, our linear regression formula, out pops this array B. Now the ordering of the three different numbers here, so we have 0.21, 0.62, and 1.96. That's A, B, and C. And the reason they came in that order is because we put in our columns of the matrix X, we first put a column corresponding to x squared, and then x, and then 1, in that order. So for B, our first parameter that we get out is the coefficient for x squared, and the second one is the coefficient for x, and the third one is the coefficient for 1, or in this case just the constant c. So our resulting fit is 0.21x squared plus 0.62x plus 1.96. So let's see what that looks like, that linear regression result. Well, it looks pretty good. Okay, so let's try a slightly more complex example. So suppose now we have this data here, and let's plot that to see what that looks like. So that's a little less straightforward what that might be, but suppose we know, we have a hunch that this is sinusoidal data, and we want to fit to that y equals a sine x plus phi. So our two parameters for this fit are a, the amplitude of the sine wave, and phi, the phase. Well, here we come into a problem. You know, when it was a lot easier with y equals ax squared plus bx plus c because that was linear. In that case, you could isolate the variables from the parameters, the coefficients that we were trying to fit, the a, the b, and the c. Here, we can't write this as y equals a times some function of x plus phi times another. That's what you need in order to do a linear regression. So it's not clear how we can do this. But recall the trig identity for the addition of sine functions. If we have sine a plus b, that's equal to sine a cosine b plus sine b cosine a. Now let's see how this comes in handy here. We can rewrite a sine x plus phi as a cosine phi sine x plus a sine phi cosine x. And notice that we have these coefficients now in front of sine x and cosine x, and if we relabel those as b and c respectively, now we have b equals a cosine phi and c equals a sine phi, then we can rewrite this y equals a sine x plus phi as b sine x plus c cosine x. And sure enough, now in red we have the parameters of this fit, this b and c, and in blue we have the functions of x. So we've separated the functions of x with the parameters. So now, if we want to build up a matrix X, our first column is going to correspond to our sine of X and So which means that in B, the first variable that we get out from our result B, the first row of B will be this parameter B. And our second column will be the cosine x data. So that's x. And y, again, is just simply our y data from the xy data that we had originally. And so now if we plug in our linear regression formula, we get b equals 2.89 and 4.18. So 2.89 corresponds to the coefficient for the sine x term, and 4.18 corresponds to the coefficient of the cosine x term. So here's our function, here's our linear regression fit for our xy data. And let's see what this plot looks like. So here's our original data. Not so easy to see a trend, but if we plot our linear regression on top of it, again, it looks pretty good. Now, a little further work. So we want to reconstruct A and phi. We want to know what our amplitude and our phase were, but instead we got these numbers B and C. So we got B is equal to A cosine phi, and we got our result from the linear regression of 2.89. And C we got as being 4.18. So is it possible to reconstruct A and phi from these two numbers? Well, you can see how to get A by adding B squared plus C squared and taking the square root. So if we do that, then what we can do is we can factor out the A squared from these two terms under the square root. And now we're left with A squared times sine squared phi plus cosine squared phi, all under the square root. And remember, recall that sine squared plus cosine squared is equal to 1. So that goes away, and we're left with A. So A is equal to the square root of B squared plus C squared. And if we plug in those numbers, we get 5.08. And we can similarly reconstruct phi by, well, if we could get those A's to cancel, if we could divide C by B, then the A's will cancel, and we're left with the tangent of phi, because sine over cosine is equal to tangent. So we can get phi by taking the arctangent of C over B, and that gives us 0.96. So now we have both the amplitude and the phase. So what we've done with linear regression here on the left, we've done a more straightforward parabolic fit or quadratic fit. And on the right, we've looked at a more complex function, this sine wave, where it's not obvious that we can do linear regression because it's not obvious that this isn't a linear function like a quadratic would be. But by using some cleverness and some trig identities, we were able to do linear regression on both of these. All using this very simple relation that you take your x data, you take your y data, you plug it into this formula, and you get the parameters for your linear regression.